First of all, just the idea of a field in general. The idea of a field is very closely related to the idea of a function for mathematics. When we say something is a function, like let's say if we write y is a function of x, what do we mean by a function of x? When we say something is a function of another variable, what does that actually mean? Or to put it another way, how would you check if something really counts as a function or not? Yeah, you could think of the x as the input and the y as the output. So a function is just an operation that takes some input and assigns an output to it. Specifically, it assigns exactly one output. Every input gets an output, and every input gets only one output. You're not going to get several different outputs from the same input. So if you think of this as an input and an output, a function is just some operation that assigns exactly one output to every input. And specifically, we typically assume the input and the output are both numbers. They don't necessarily have to be numbers. You could have a function that takes anything as an input and produces anything else as an output. But we typically think of them as numbers. So an operation that assigns an output number to each input number. Whereas something would not count as a function if it assigns several different outputs to the same input. Although, of course, it's totally okay for several different inputs to be given the same output. For instance, if your function is x squared, 3 and -3 as inputs would both lead to the same output. F of 3 would be 9, f of -3 would also be 9. So it's totally okay for several different inputs to have the same output. We just don't want one input to lead to several different outputs. A field is basically the same idea, except in a field, we're specifically talking about positions as in locations in space. A field is a quantity that has one value at each location in space, each point, each position. So this is very much like a function, except instead of having a number as the input, it has locations in space as the input. So we're basically looking at a value for each location in space. And that value could be a number, a scalar, or it could be a vector. You could assign a vector to each location in space, or you could assign a scalar to each location in space. So we typically call those a scalar field versus a vector field. So a scalar field, the output is a scalar, just a number, presumably with units of measurement, versus a vector field. And in both cases, we're still using a location in space as the input. But for a vector field, the output is a vector quantity of a magnitude and direction. Any questions on that definition so far? Just the basic terminology there. So what would be some examples of a field? What would be some examples of some quantity you could assign to like every location in a room or every point on a map? Yeah, a temperature map is a good example of this. Like if you take a look at a weather report showing a map, maybe you have like a map of California, for instance. This is the most important thing about a map of California, by the way. As long as you got the Tahoe angle right, you can draw the rest pretty much however you want. Of course, you also want the day. But as long as you got the Tahoe angle and the bay, the rest of it's obvious in California. But on a temperature map, you could have just listings of temperature in various different locations. And there's several ways you can write this. You could just maybe list out a grid of numbers. Maybe here it's like 50 degrees. Here it's 52 degrees. 52 degrees also. Maybe 58 degrees. 60 degrees. 70 degrees, something like that. So maybe something like that. You could just list out the temperature at various locations by just putting numbers on the map. Or alternatively, sometimes you might draw this. What's another way you could depict the temperature more visually rather than just drawing in a bunch of numbers? Yeah, you could depict this with colors. And in particular, you could assign a color gradient to different temperatures. Like maybe lower temperatures are depicted as more blue, higher temperatures are depicted as more red. And you've got a gradient of like blue, blue, violet, violet, red for different temperatures. So maybe the lower temperatures we could color in blue. And then the more medium temperatures we could color in purple. And the higher temperatures we could color in red. Or maybe orange. And so this color map, sometimes called a heat map because it's similar to, I mean, not only if it's just mapping out temperatures, but any idea where you're associating colors with values of the scalar would be often called a heat map or a color map, where each color represents a certain value or a certain range of values. So that's often a much more visually useful for in just interpreting by looking at it what's going on. But that is one way to depict a field. Another way is to draw in lines representing certain values. For example, if you notice that there are certain connected regions that are all at the same temperature, like maybe you happen to know that everything along this region is all at about 60 degrees. You could draw in a curve representing all those points that are at 60 degrees. And maybe you find that as you go further south, it gets hotter. So maybe you've got another band of region where it's all at 65 degrees. And then another band where it's all at 70 degrees. And then maybe there are some mountains changing that around. Or wherever the temperatures are. But the idea is if you notice a connected region of locations that are all at the same temperature, you can just draw a sort of a band connecting those and say, this is the region where the temperature is all 60 degrees. And then this would be the region where the temperature is all 65 degrees. And assuming this is continuous, then if you have a point between those, we can say, well, we don't know exactly what the temperature is there, but it's somewhere between 60 and 65. So this is another useful way to graph or to draw a diagram of values of a field. You can draw in a curve representing all the locations that have the same value. And this is usually called an equisomething curve. In this case, we might call it an equithermal curve. I guess sometimes in this case, it could probably be called isothermal. These would probably be called isothermal curves. These are regions where everything's at the same temperature at all of those locations. So those are usually called an isosomething curve or an equisomething curve. And we're going to be especially looking at this sort of depiction when we get to the idea of voltage. If you want to map out the voltages everywhere in space, not just voltage along a wire like we were looking at 7b, but voltage everywhere in space, it would be inconvenient to write out the voltage everywhere on a grid. So instead, we just draw some curve representing all the points that are at 5 volts, and another curve representing all the points that are at 6 volts, and so on. Those would be called equipotential curves. And that would just mean all points that are at the same voltage. Since potential or electrical potential is just another word for voltage. So this is one way of describing or visually mapping out a field, specifically a scalar field. And temperature is one good example of that. Are there any other values that you might associate with every location in space or every point on a map? What are some other fields that could potentially be mapped out? Like, for instance, sticking with this analogy of a map of California. What are some other, elevation would be a good example. You might have a map that shows like a topo map showing the elevation everywhere on the map. So maybe you have a map and maybe everywhere on the map it lists the elevation. But again, it would be inconvenient to try and just write out a whole bunch of numbers showing or just listing the elevation everywhere. So what we would typically do instead is draw in lines representing a constant height, equal altitude lines. So for instance, let's say we've got the Sierra Mountains over here. Maybe all of these points represent the same very high altitude. And then maybe this is an even higher altitude. And then over here, we've got lower altitude. And I guess the Central Valley is probably going to go in here somewhere. We got the lowlands of the Central Valley. And then the transverse range over here. So each one of these curves represents all points at the same altitude. So maybe this curve represents all the locations that are, let's say, 100 feet above sea level. And then this curve, every point that is 200 feet above sea level. This curve, 300 feet above sea level, and so on. So if you are traveling along one of those curves, you're not going uphill or downhill. You're just staying at the same elevation. But if you travel perpendicular to one of those curves, you're going uphill or downhill very fast. So this is another useful example of a field. The elevation, the location, the elevation at every point on the map is a field. It's assigning a value to each point in space. And would that count as a vector field or a scalar field? If you're listing out the elevation, do you have to attach a direction to it, or are you just listing a number? Yeah, this is a scalar field. I mean, technically, I guess you could say it has a direction. It's upwards above sea level, but since it's all listed as above sea level, the direction doesn't really matter. On the other hand, what would be an example of a vector field? What would be a quantity you could list at every location on this map that does have a direction associated with it? Yeah, wind velocity would be a good example. If you wanted to list out the velocity of the wind, taking another example from the idea of a weather report, you could list out wind as how fast it's blowing and in which direction it's blowing. So presumably you draw that by just drawing out a bunch of vectors. I'm just making up some examples here, but you could draw out just a bunch of arrows on this map showing the general, showing the direction and magnitude of wind velocity at each location. So at this location, maybe the wind is blowing due west moderately fast. At this location, maybe it's blowing south-southwest very fast. Here, maybe it's blowing west very slowly. And so this would give you a very accurate depiction of wind velocity at various different locations. And this would typically be called a field vector diagram. But it tends to get very cluttered. If you're drawing out the vectors everywhere, it tends to be very cluttered in terms of, I mean, it takes a while to draw out. It's kind of awkward to try and interpret the information. So often for vector fields, instead of drawing out the individual vectors, we would draw this as what we call field lines. So let's say we're looking at the exact same situation. But instead of drawing out the individual vectors as individual arrows, we can just draw out the general trends. The trends seem to be sort of northwest and then curving to the west or southwest. So the general trend, instead of drawing the individual arrows, we just draw the overall curvature. with arrowheads on the curves themselves to give an idea of directionality. But this makes it much easier, once you get the hang of it, much easier to read and interpret what's going on here. Instead of drawing a bunch of individual arrows, we just draw the general trends. So this would be called a field line diagram. And one of the useful ideas of this, if you do need to know what's the actual vector at any given point, like let's say you want to know what's the actual vector at, let's say, this point. You could just draw in an arrow tangent to the field line at that point. Any questions on those diagrams so far? And these both have their uses. The field vector diagram versus the field line diagram, they're both supposed to be representing the same information. The field line diagram is typically easier to read, again, once you get the hang of it. But what information do we kind of lose here? What information is portrayed by the vector diagram that is not exactly portrayed by the field line diagram? Yeah, the magnitude isn't really displayed so well. The field line diagram is great for showing you the direction everywhere, but it doesn't really show the magnitude of the vectors in as much detail as the field vector diagram does. The way we account for that, or sort of partially make up for it, is that in a field line diagram, magnitude is represented by the field line density. That is how closely packed together the field lines are. So in a region where the field lines are very spread out, that's supposed to represent that the field magnitude is weak there. Whereas in regions where they're packed very close together from side to side, that's supposed to represent a region where the field is strong. So field lines close together mean the magnitude is strong in that region. Field lines spread further apart means the field is weaker in that region. And then this isn't really very well drawn. I haven't really drawn this density to correspond to the size of these vectors, but that's what it's supposed to be. It's supposed to be that the closeness of the lines represents the strength of the vectors, the individual magnitudes. And that's not really a hard and fast interpretation of like a certain distance doesn't really correspond to a certain strength. It's more just to get an idea of relative magnitude. Like if they're closer together in one region and further apart in another region, that tells you that this region has a stronger magnitude than this region. It doesn't really tell you what that magnitude is exactly though. But it's a good way to get an intuitive grasp of where it's strong, where it's weak, which direction it's pointing. Any other questions on the notation or terminology so far? And one other useful example I'd like to mention is the idea of gravity. If we're talking about on the surface of the Earth, which we typically have been so far, acceleration of gravity can be treated as a constant. You're always going to be accelerating towards the center of the planet at 9.8 meters per second squared. But what happens to gravity if you get further away from the planet? If you've got Earth here, if you get further away from Earth, what would you expect to happen to the strength of gravity? Yeah, it's going to get weaker. So if we were to draw out gravity, because gravity provides an acceleration. Gravity provides acceleration. This is the G in the, for instance, potential energy of gravity equals mgy. But gravity gets weaker as you get further from the planet. So let's say you are right here. The gravity acceleration vector, acceleration of gravity, is going to be pulling you towards the planet, and it'll be pretty strong. Likewise, if you're here, it's going to be pulling you towards the planet, and it'll be pretty strong. Same thing over here. Same thing over here. All of these directions, by the way, count as down because they're all towards the center of the planet. But all of these locations, no matter where you are, gravity is pulling you towards the center. But if you get further away, gravity is going to be weaker. And no matter where you are, gravity is still pulling you towards the center of the planet, but it's going to be weaker the further away you are. And this is true no matter where you are. It doesn't have to be in these 8 cardinal directions sort of thing. No matter where you are, the further you are from the planet, the weaker gravity is going to be. But it's always going to be pulling inwards towards the center. So these would be some of the field vectors in the field vector diagram, all pointing towards the center of the planet, but getting weaker and weaker the further you get. And these are acceleration vectors, which is important because if we thought of gravity as a force, let's say you've got 2 objects. Like let's say you've got an astronaut and you've got a space station. An astronaut and a space station at the same location in space. What would you expect about the force of gravity on those 2 objects? Are they going to be experiencing the same force? Because what's different about them? What's the big difference between these 2 objects? Yeah, they have different masses, right? Exactly. Force of gravity equals mass times acceleration of gravity. And those should, of course, be vectors. Both of these objects experience the same acceleration, the acceleration of gravity at that location, but they have different forces. They experience different force of gravity because they have different masses. So this is an important distinction here. They both have the same acceleration because they're both at the same location in space. Any object placed at this location is going to experience the same acceleration, but will experience different amounts of force because force depends on mass. So if we want to categorize these, we would say force is a property of the object. This is a property or something felt by the object. And it is mass dependent. Different objects will experience different forces because they have different amounts of mass. But the acceleration, this is mass independent. Any objects, even if they have different masses at this same location, will experience the same acceleration. So acceleration is not a property of the object. It is more a property of the location in space. And this is why we would call the gravitational acceleration a field, the gravitational field. It counts as a field because it is a property of the location in space. Every location in space has an acceleration vector associated with it because of gravity. That acceleration vector has nothing to do with what object is there, or even if there is an object there. This location has a value of acceleration of gravity caused by the Earth. If you also put an object there, that object experiences a force associated with that acceleration. But the force is a property felt by the object, which depends on its location and its mass. Whereas the acceleration is just a property of the location, regardless of the object that you put there, or even if there is an object there at all. So this is why we'd say acceleration is a field, but force is not. Acceleration is just a property of the location in space. Force depends on that and the mass of the object we're using. So that's one of the big distinctions here. The acceleration, property of a point in space, versus the force, a property of the object we put there. Any questions on the distinction between those? And by the way, if you solve this for acceleration, what would you get? Yeah, you get force divided by the mass of the object. So that means the acceleration vector can be calculated by measuring the force that the object experiences, which is a property of the object, and then dividing by mass. So we're basically taking a property of the object, but dividing by how much mass the object has. That sort of cancels out the dependency on mass. And what's left is a property of the location in space, regardless of the mass of the object that is used. So different objects will experience different amounts of force. The astronaut experiences a fairly weak force. The space station, being more massive, experiences a stronger force. But if you take the ratio of force over mass, so force on the astronaut over mass of the astronaut, and force experienced by the space station divided by the mass of the space station, those ratios will be the same. Because the ratio, the acceleration, is a property of this location in space, not a property of the object depending on mass. Any questions on that so far? And this, by the way, could also be drawn as a field line diagram. Instead of drawing out the individual vectors, we could draw in a field line or a collection of field lines representing the general trend. All these vectors were pointing inwards towards the center. So if we just draw in field lines pointing inwards towards the center, this would be the field line diagram of Earth's gravity. And of course, it should really be three-dimensional. We should have lines coming in from other directions three-dimensionally as well. But this is a two-dimensional cross-section of it anyway. And so the field lines with arrowheads tell you the overall trend in the direction of those acceleration vectors. Also, how would you get information from this diagram about the magnitude of acceleration at different locations? Without being able to see the size of the vectors, how could you still get information about magnitude? Yeah, the density of those field lines. And I think it might be easier to see if I draw in a few more, if I fill in these in-betweens. And you want to fill in the in-betweens evenly if you want to add more detail. You don't want to make it lopsided. So if we take a look, for instance, at, let's say, this region of space versus this region of space, the field, even though these are the same amount of space, here we've got 1, 2, 3, 4, 5 field lines passing through. Here, same region of space, but we've only got 3 field lines passing through. The field lines are more spread out. Here, they're more concentrated. So in the region where they're more concentrated, packed more closely together, that is a stronger magnitude. Out here, the field lines are spread further out, so that is an indication that the field is weaker in that region. And this matches with what we should expect. Gravity should be stronger when you're near the planet and weaker when you're further from the planet. Any other questions on that so far? Then let's see if we can apply the same principles to electric forces instead of gravitational forces, using some of the same techniques. Let's say we have a couple of charged particles, because electric forces depend entirely on the charges of the objects. Let's say we've got some charged particle. I'm going to call this positive capital Q, and some other charged particle positive lowercase q. So 2 charged particles, big Q and little q, just represent their charges. What would these objects do to each other? Yeah, they're going to repel. They're going to experience forces in outwards direction. We're going to have the force, let's say the force of, we call these objects A and B, for instance. We've got the force of A on B. And we've also got the force of B on A. And what would you expect about those forces? How do those forces relate to each other? Are they the same strength, or is one stronger than the other? What do you think? Yeah, these are exactly the equal and opposite forces predicted by Newton's third law. The force of A on B and the force of B on A should be exact opposites according to Newton's third law. So that's what we should expect here, equal and opposite forces. And since they're equal and opposite, we don't really need to keep track of both of them. We know they're going to be the same magnitude. We know they're going to be opposite directions. So we could focus on just one of them. And typically what we do is we pick one of the charges to analyze. We want to know, let's say, the forces on this object. We would call that the test object or the test charge. And the other one, even though these are exerting forces on each other, we're going to think of this as just object A exerting a force on object B, and we don't really care about the other force. So ignoring the force of B on A, we're going to call A the source object or source charge. The outline of the ideology here is, even though these objects are exerting forces on each other, we're going to treat one of them as creating some sort of effect, and the other one as experiencing a force from that effect. And this is interchangeable. We could treat object B as the source charge, creating some effect that causes a force on object A as the test charge. So it's not like source charge and test charge are two fundamentally different kinds of charge. It's just a matter of our own point of view. The one we call the source charge is the one we're thinking of as creating some sort of effect. The one we call the test charge is the one we're thinking of as experiencing a force from that effect. But again, this is completely reversible. You could change up what you're calling the source charge and what you're calling the test charge, and you get equivalent results. It's just a matter of which one you care about in terms of forces acting on. Any questions on the terminology there so far? So let's investigate, let's say we have one big source charge. Let's say we have just some big positive source charge way over here. And we don't even really care where that is. There's just some gigantic positive charge way over here somewhere, the source charge. And typically the source charge we're assuming is staying still. Maybe it's fixed in place by some sort of structural framework, or maybe it's so massive that it's hardly going to move at all, even though there are forces acting on it. Or maybe it is moving, but we just don't really care about its motion. We want to figure out what effect that has on some other charge over here, the test charge. So let's say we put a charge here, which we're really calling the test charge because we're using it to test out what's happening at that location. And let's say we have a charge that is, let's say, 6 coulombs. Let's say we have a 6 coulomb charge, and we measure the force acting on it, and we find that the force is presumably to the right. And let's say that force is, let's say 15 newtons. But let's say we use a different charge. Let's say the 6 coulomb charge experiences 15 newtons of force. Let's say we take that charge away and put a different charge in the same location. Let's say a 12 coulomb positive charge in the same location. How much force would you expect that charge to experience? Yeah, it's got twice as much charge, so presumably it experiences twice as much force. Everything else is the same. It's experiencing an effect from the same source charge. It's in the same position. If all we're doing is doubling the charge, we should expect the force to also double. So presumably that'll be 30 newtons. Or what if we tried a charge of, let's say, 2 coulombs? If the charge is only 2 coulombs, how much force would you experience? Or how much force would you expect? Yeah, it's a third as much charge, so we should expect a third as much force, only 5 newtons. Or what if we had 4 coulombs? Or to make it interesting, let's say -4 coulombs. If the charge is -4 coulombs, what would you expect the force to be? How much force would you expect there? First of all, the negative suggests that the force is going to be in which direction? Yeah, it's going to experience a force to the left. Intuitively, we should expect the positive source and the negative test charge to attract each other. So this is going to experience a force to the left. And how would you determine how strong you'd expect that force to be? Yeah, it should be 10 newtons in that direction. One way to see that is it's twice as strong as this charge, so we should expect twice as much force. Or you could say it's a third as much of 12 coulombs, so it should be a third as much force as that 30 newtons. Either way, force is going to be, and I would still write the magnitude as a positive number, because magnitude is like absolute value, but the direction would be to the left instead of to the right. So we've got all these different charges experiencing different amounts of force, even though they're all in the same situation. Any questions on that so far? And it appears that in general, all of these expected values are really just based on the idea that the force is proportional to charge. We've been assuming all along, and this is a correct assumption as it turns out, that the force on the object is proportional to the charge of that object. Force is proportional to, I'm going to write this as test charge. And of course, the source charge is going to be involved as well, but we're ignoring the source charge for the moment. We're just saying there's something causing this effect on all these charged particles. And the amount of force they get is proportional to how much charge they have. But what does that mean? If we say two quantities are proportional, like if we say y is proportional to x, then how would we write that as an equation? If y is proportional to x, what equation can you write out for sure? Yeah, y equals some constant times x. And that might be, that constant could be anything. It might be, maybe it's mass, maybe it's something else entirely. Could be any value depending on the circumstances. So if we were saying that force is proportional to charge of the test object, that suggests force equals charge of the test object times something. Some mysterious quantity that we can multiply by the charge to figure out the force it experiences. And that something we're going to label capital E. So capital E here, this electrical quantity, which is why we're calling it E, is the multiplier that we multiply by the test charge to figure out how much force the object experiences. Also, force has to be a vector. Is charge a scalar or a vector? Yeah, charge is a scalar. It can have a positive or negative, but it doesn't really have a direction. So does E have to be a scalar or a vector to make this work out properly? Yeah, E is going to have to be a vector. The direction that force has to come from somewhere. So if force equals Q times E, but Q is a scalar, then E has to be a vector. Because now we have a scalar times a vector equals a vector. So E is this vector quantity that can be multiplied by the charge of the test object to figure out the force. And let's get some more information about this, because we've just introduced a new constant of proportionality. Anytime you introduce a new quantity like this, there are a few things that are good, a few techniques that are a good way to get more information about it. For instance, how can we get more information about what this E actually means in this context? What are some good techniques to try out to figure out what this variable actually means? Yeah, one way would be to solve for it. If we just divide by Q, we get E equals F over Q. So E, this electrical vector, can be thought of as a ratio of force over charge. So you could say this is what E means. E, this E vector, is the ratio of how much force the object experiences divided by how much charge it has. And in that context, we can actually calculate it for all of these. If we just take force divided by charge, 15 over 6, that reduces to 5 over 2, so that'll be 2.5. And that'll still be to the right. And what would the units be for that? Yeah, we're taking 15 newtons divided by 6 coulombs, so that's newtons per coulomb. And you'd think that this would at some point have been named after some dead electrical physics pioneer from the 1700s, but apparently it hasn't been yet. So it's just newtons per coulomb. And likewise for this one, if we do the same thing, force divided by charge, 30 divided by 12, what's 30 divided by 12? Also 2.5. And likewise, 5 divided by 2, still 2.5. In fact, even for this one, 10 newtons to the left, because we got to be careful about direction here, 10 to the left divided by -4 would be what? Yeah, still 2.5, but in which direction? Yeah, if we take a vector to the left, but multiply or divide by a negative scalar, that reverses the direction. So still 2.5 newtons per coulomb to the right. So even though these objects all experience different amounts of force, because they have different charges, the ratio F over Q is the same for all of them. That ratio is the same because the ratio, once again, we're taking a property felt by the object, but we're dividing by another property of that object to cancel out dependency on charge. The amount of force depends on how much charge the object has, but if we divide by charge, that cancels out the dependency. So what's left doesn't depend on the charge at all. E is a property independent of charge. It's just a property of the location in space. If we put any object here and took force divided by charge, we get the same result. So if this is a property of the location of space, what do we call it? What do we call a quantity that has a value at each location in space? That's a field. So we call this the electric field. That's really what the electric field is. The electric field is a property of the location in space, whether you put a charged particle there or not, that is equal to the ratio of the force that would be felt by a charged particle divided by its own charge if you did put a particle there. I tend to think of E as measuring the capability of that location in space to provide a force on a test particle if you were to put one there. And why is this one to the right? We're calculating force vector divided by charge. The force vector is to the left, but anytime you multiply or divide a vector by a negative scalar, it reverses the direction. So a vector to the left multiplied or divided by a negative scalar gives you a result to the right. Any other questions on that so far? So once again, electric field is a property of the location in space, regardless of whether you put a test particle there or not, and this is why we call it a field. And it is essentially telling you the ratio of the force that would be felt by a charged particle if you put one there versus its own charge. In fact, a very useful way to think of quantities that are defined as ratios like this, what's the easiest denominator to divide by? 1. So if you imagine a 1 coulomb charge, specifically positive 1 coulomb, Force divided by 1 doesn't actually change the value. So you could think of the electric field as the force that would be experienced by a 1 coulomb positive charge if you were to put one there. If you're not sure which direction the electric field should point, imagine putting a 1 coulomb positive charge at that location and ask yourself, which way does that one get pushed or pulled? That direction is the direction of the electric field at that point. Any other questions on that so far? All right, then we will look at more examples and details of how to use this next time. In the meantime, let me know if you have any other questions, and I will see you later.